Section 12.6 is triple integrals and cylindrical coordinates. This is more or less an extension of integrals in polar coordinates. We're just adding the z-axis now. So we'll look at cylindrical coordinates as a point r, theta, z, where r and theta are exactly the same polar coordinates in the xy plane that they have been in the past when we deal with polar coordinates. And z is simply equal to z. It's the directed distance of the point r, theta, z above the xy plane. In other words, that vertical distance coming up from the xy plane or downward. So a point in polar coordinates in 3 dimensions looks like the following. We first sweep out an angle with the positive x-axis. That would be this, theta, right here. And then we travel a distance r in the xy plane. That's this length along the red dotted curve. And that gets us to r theta in the xy plane. And then we move up a distance z. And that is our, this should be perpendicular or orthogonal to the xy plane, but we're directly above that red point in the plane at the blue point, r theta z. So this is our point in cylindrical coordinates. So let's move on and convert explicitly. So this will look a lot like what we've done in the past. X is r cosine theta, y is sine theta, y is r sine of theta, r sine of theta, and z is equal to z. Okay, so that being the case, we've also got the reverse, going from rectangular to cylindrical coordinates. We have r squared is equal to x squared plus y squared. Tangent theta satisfies the relation y over x, or is equal to y over x, and z equals z. So all things as usual, we just have a third component to deal with each time, which turns out to be a very easy conversion for these cylindrical coordinates. So we're asked in the example below to plot the given cylindrical coordinate and find the rectangular coordinates of the point. So we're given 2, negative pi over 2, 1. One of the things that, one of the harder things about this is just remembering what's what. It's r theta z, so this is r, the angle theta, and the value z. So it's best to plot r theta first. Z is usually pretty easy to pick up, but theta from the positive x-axis is negative pi over 2, so we sweep this way towards the negative y-axis for an angle of 90 degrees, or pi over 2. It doesn't quite look that way because of the perspective looking into the 3 dimensions that we've rendered here in the plane. And we travel outward a distance of r equals 2. And then we will finally pick out z's component, move up a distance of 1. So we move up a distance 1 above that point in the xy plane. And that's our given coordinate, 2, negative pi over 2, 1. To convert this to polar coordinates, it's always a good idea to have an idea of where this point is in terms of the xy axis, so that way we can pick the correct angle theta to represent the polar coordinate. So with these values given, we have x equals r cosine theta, and 2 cosine negative pi over 2. Cosine negative pi over 2 is 0, so that just comes out to 0. Well, actually, in this case, the formulas, since we already know theta, we're not worried about finding theta, so excuse that. The next problem, we will want to know what quadrant we're in the xy plane. Now, y is r sine theta. Moving from cylindrical to rectangular coordinates is just as easy as polar to rectangular coordinates, just following these formulas we have here. 2 sine negative pi over 2 is 2 times negative 1, so that's negative 2. Okay, and then z is just equal to 1. Extracting that directly, easy conversion every time. And we've got 0, negative 2, 1 for our rectangular coordinate x, y, z. Okay, going the other direction. This is where we want to be a bit more careful about which quadrant we're in and how to pick our angle theta. So we're given the rectangular point, negative 2, 2 root 3, 3 as x, y, z respectively. So immediately we can convert z. So we just make a note off to the side, z equals 3. So we're done with that. All we need to worry about now is x and y. So really let's render x and y in the xy plane. We know that z is 3. It's above that somewhere along the z-axis, and then we'll get to that in the very end. Now, negative 2 on the x-axis, and then positive 2 root 3 on the y-axis, leaves us in quadrant 2. This puts the angle theta swept out from the positive x-axis to the terminal side, the terminal angle that we're dealing with. And this is, well, tangent of this angle theta is equal to the y value over the x value, so 2 root 3 over negative 2. That's just looking at this as the triangle that we're given here. And this is exactly what we have in this expression. And now that's tangent theta equals negative root 3. However, we evaluate that or recall that this is the angle 2 pi over 3. So in other words, that is an angle that satisfies this equation. If we just used arctangent, we would end up with an angle down here. It would be negative pi over 3, thanks to the range of arctangent and how it's defined. But we know that we must be in quadrant 2. So whatever this angle here might be, we have to add pi to it and bring it back around to 2 pi over 3 as we got. However you go about finishing the details of that is fine, but we do need to be in this quadrant. So we know it's 2 pi over 3. Okay, so that's theta. The last thing to find is r, and that's pretty straightforward. R squared equals x squared plus y squared. So we've solved for r as the square root of x squared plus y squared. Comes out to root 16, which is 4. So our cylindrical coordinate of this rectangular coordinate is r equals 4, theta is 2 pi over 3, z is 3. So 4, 2 pi over 3, 3. Okay, that's converting back and forth between two coordinates. Just to be sure we have the basics of this. We had to see a couple of those examples. Now let's look at graphs. Determine the graph of each function expressed in cylindrical coordinates for some constant c, some real number c. Okay, if r is equal to c, the radius is the only thing with a constraint in this equation. It's equal to c. Well, that tells us something about, it's a circle, right? It's a fixed radius of c. So it must be a circle centered around the z-axis, only z is also allowed to vary up and down the z-axis. So that circle is extended along the z-axis to form a cylinder. To see it a little bit further, r is equal to square root of x squared plus y squared. That's all equal to c on the right-hand side still. Square both sides, x squared plus y squared equals c. That's a circle of radius c. And with the z variable free to vary from 0 to infinity or negative infinity to infinity, we have a cylinder with center axis, the z-axis. Okay, next, another similar problem. We have z equals c. So just a lot of simple looking equations here that we're looking at. Z equals c is exactly what we would think it would be. It's all the points r, theta, c in cylindrical coordinates. There's no constraint on r and theta, so they can be any values. The only thing that needs to be fixed is the c value. So we're at a height of c above the xy plane or below it if c is negative, and that's just the plane, more or less as we would expect. It's the only one that carries over in rectangular coordinates as well. Z equals c in rectangular coordinates is also a plane. Now down below, the last simple looking one is not so simple. Z equals r, z is equal to the radius. So again, r is the square root of x squared plus y squared, so we swap that out on the right. That squaring both sides is equivalent to z squared equals x squared plus y squared. Now, r is positive, then we see here that this must have been positive, so we have the top half of the cone, z equals square root of x squared plus y squared, and if it was negative, then we'd have the bottom half. So either way, it's a portion of the cone. It'll be clear in any problem that we're dealing with which part of the cone we're actually interested in. Okay, so evaluating triple integrals with cylindrical coordinates. Now we're getting into the calculus of these situations. So what we'll want to do, and the reason to use cylindrical coordinates is because our projection of some solid E in three-dimensional space onto its projection D onto the XY plane might be more conveniently described in polar coordinates. Basically, if things are circular, if we have circular, semicircular, or quarter circular projections onto the XY plane, then we're going to want to consider cylindrical coordinates to handle this, because we can sweep out this projected region in terms of these coordinates and simplify, hopefully, the integral we're dealing with. If it doesn't simplify the integral, then it's probably not a good choice to use cylindrical coordinates. So we'll describe E as its projection. It's the points x, y, and d, where d is described as a in polar coordinates. And then z is bounded by two surfaces, u1 of xy and u2 of xy, below and above respectively. And we will convert those to polar coordinates as needed. That's a pretty direct conversion, we'll see below. So we're looking for the integral of this function over the solid E. Then we can peel off that first integrand, express it with respect to z of f of x, y, z, bounded by the surfaces u1 to u2, functions of x, y, the lower and upper limits of integration, respectively. And then we integrate the rest of this with respect to d. So we could even do this in rectangular coordinates if it seemed appropriate. We typically won't. None of the example problems or exercises that I've seen do that. So everything will convert to polar coordinates, even though it doesn't have to. Now, things that are necessary is that we do follow this formula quite clearly. So this is our conversion of our integral of the function f over the solid region E. And we swapped completely. This is d's constraints, the outer two integrals for dr d theta. And this is z's constraints that we have here. So when we convert x and y rectangular coordinates into r theta, x is equal to r cosine theta, y is equal to r sine theta. So there's x and there's y respectively in each of the arguments of u1 and u2. We also convert the arguments x, y, and z, x, y, and then z is just z, to polar coordinates or cylindrical coordinates as well. The r is from the polar coordinate integral r dr d theta. That's what we did back in 12.3, polar double integrals over polar coordinates. And then we have dz, of course, to range between u1 and u2, the surface bounds. Pretty much every example and exercise we do and see in this section will be in this order. Most notably, dz will be integrated first. We'll always cap z above and below with limits of integration, integrate that one first. It just seems to be the way these examples work out, and it's part of simplifying integrals using cylindrical coordinates. So just a reminder of what's going on with dv. Remember, dv is the infinitesimal volume when we have these sub-cylindrical rectangles now, we'd call them. This is a cylindrical rectangle drawn below, this little wedge-looking piece here, or piece of a cylinder, we might see it as. dr is the change in the radius, so that's one dimension of dv. r d theta is that arc, r times d theta being the angle swept out between the two dotted lines, and r d theta being the arc length, is exactly our infinitesimal arc length contribution. And then that times dz, the thickness or the height of this little wedge, all times each other gives us dv. So it's a nice reminder for how this formula works, particularly to include the r that shows up in this formula right here. So that loose multiple of r comes about because of r d theta and that volume wedge or subrectangle. So let's use the formula. Okay, so evaluate the triple integral of the function f of x, y, z equals square root x squared plus y squared. Already we see something that looks like it might be useful to use cylindrical coordinates for, because polar coordinates will simplify x squared plus y squared to the power of 1/2. We'll see that in a moment. This is integrated within the solid E, which lies within the cylinder x squared plus y squared equals 1, under the plane z equals 9, and above the paraboloid 1 minus x squared minus y squared. This looks perfect for cylindrical coordinates. We see lots of squared variables, particularly x squared plus y squared in a few different places. So that's nice. Z has nice simple boundaries. Above it, it's bounded by the surface z equals 9, which is just a plane parallel to the xy plane. And below, it's bounded by the top, or bounded by sort of the local maximum portion of the parabola z equals 1 minus x squared minus y squared. Remember that this highlighted function is in fact a paraboloid, opening downward, centered at z x y, or centered at the origin 0, 0, 0, more or less. So it's got central axis 0, 0 in the xy plane. Okay, to describe it, we just say that x and y are just arbitrary points in D, and we know that z is capped by 1 minus x squared minus y squared on the bottom and above by 9. Okay, now we need to express D in a more clear way. D is the set of points x, y such that x squared plus y squared is less than or equal to 1. That is this constraint, that it's within the cylinder, x squared plus y squared equals 1. And this is what's given to us here in the last two constraints, just to make those connections. Let's convert it all to cylindrical coordinates. We do this because we're dealing, one, with a cylinder, either told or not, or just recognize that that's a cylinder. And we're dealing with things that will convert very nicely to cylindrical coordinates, so it's certainly worth a try to see if that will simplify the process. So cylindrical coordinates in this case, we note first that 1 minus x squared minus y squared, looking at this piece, has 1 minus this group, the sum of x squared plus y squared, and x squared plus y squared is r squared, so this comes out to 1 minus r squared. So already this simplifies z's lower bound for the region E. So that's nice, we'll include that. There's nothing to change for its upper bound of 9, that's simple enough. And we'll note that this region is a circle centered at the origin, 0, 0 in the xy plane, with radius 1. So this is exactly theta and r values for a circle of radius 1, or all points within a circle of radius 1. So we've got the region D described, and we've got E fully put together here. So we can use this to set up our integral. So our integral over the region E of our given function, we note that this function, x squared plus y squared, square root of all that, is root r squared, which is just r. So it's a very nice simplification in our integral. Once we've converted, we know that theta goes from 0 to 2 pi. So there's d theta's limits. We know that dr, r goes from 0 to 1. So there's the limits along the r-axis. And we know that z ranges from 1 minus r squared to 9. And that's this range here. And of course, we're integrating dz, dr, d theta. Again, like I mentioned before, this will pretty much always be the order of integration. dr and d theta can be swapped pretty regularly, pretty handily, to not much of a difference in convenience if you do so. So this is the r from this integrand, and the other r is from the integral formula, r dz, dr, d theta. So we don't want to forget that extra multiple of r in every one of these cylindrical coordinate integrals. So integrating with respect to z first, we introduce the variable z, and that is from 1 minus r squared to 9. So limits of integration plugged in look like this. 9 minus, parentheses 1 minus r squared. Then we have r squared times that. Simplifying that term, we have 8r squared plus r to the 4th. Integrating with respect to r, we have 8/3 r cubed plus 1/5 r to the 5th from 0 to 1. And while 0 is not going to contribute anything, it'll be minus 0. And then r is just, when r is 1, we have 8/3 plus 1/5. I've moved that constant out to the front of the integral. So 8/3 plus 1/5 is out front, times the integral 0 to 2 pi of d theta, which is just theta evaluated from 0 to 2 pi, which is 2 pi minus 0. Common denominator here, because it's 43 over 15, and in the end, the result is 86 pi over 15. So these integrals are nice and clean and easy to do, but the tricky part is to set them up or to convert them into cylindrical coordinates in order to do so. Now, we're given an integral, an iterated integral that's in rectangular coordinates, dz, dx, dy. We see the order here. And we're told to evaluate the integral by converting to cylindrical coordinates. Now, in this case, we're not being constrained just for no good reason. We're being constrained because this integral with these limits of integration can get very messy. It could be a lot of work that we don't really want to have to do the rectangular coordinate way. So we'll rewrite it via Fubini's theorem as the integral of x squared plus y squared over some solid region E, which we'll have to parse out from all these limits of integration, with respect to volume of E. Okay, so let's start to write E down. E in rectangular coordinates is the following. That's just piecing each one of these together from what we see in the limits of integration, in the order of integration, and declaring what each variable is bounded by. So again, something about this integral with all the squared variables and square roots of things, it tells us cylindrical coordinates will probably help us to simplify the situation quite a bit. So that is our goal. So we'll compact this notation here into just saying that this is x, y, and d. Okay, and let's look at that a little further. So that's d, then d is this information here. And when we look closely at what d actually is, we see that it's y ranges from -1 to 1. X is greater than, this is a semicircle below the x-axis. This is a semicircle above the x-axis. So it traces out a full circle of radius 1. If you look off to the side, you'll notice even further that we've done some details. Well, what happens when x is equal to one of these? Oh, it's just talking about x squared plus y squared equals 1. So there's the circle we're talking about. And the thing we've done in red is actually only for the positive upper half of the plane, because we start with a positive x, presumably, and say it's equal to a positive root 1 minus y squared. Now we can do it the other way for negative x and get the same equation of the circle. Anyway, we know that this is a full circle of radius 1, so we write it down as is, and we do that in polar coordinates because it's much simpler than what we have in rectangular coordinates here. Now the next thing to look at, z is capped by 1 on the right, and it's bounded by root x squared plus y squared on the left, or below. So root x squared plus y squared is root r squared, which is just r. So it turns out z is bounded by r below and 1 above. Now we've completely converted the solid region E into polar or cylindrical coordinates. Now we didn't maybe need to split off all of this work with just D itself here. These 3 lines could be skipped in the future if you see the details of this quite well or easily enough. If not, it's a good idea to parse every region out and be sure of what you're dealing with. We could typically go from here to here once we're comfortable with this and make all these arrangements. So anyway, however we get to this, we've got the region E, so we can now integrate our given function, x squared plus y squared over E. And as an iterated integral in polar coordinates, we'll go from 0 to 2 pi for theta. We'll go from 0 to 1 for r. And z is bounded by the surfaces r to 1 for dz. And our function, the last thing to note is our function x squared plus y squared is equal to r squared. So we'll make that substitution here. We convert everything to polar coordinates. Now the loose factor of r is part of the integral formula for polar coordinates. It's always there. It's r d theta essentially, only we've commuted d theta out to the end of the chain there, as we usually will. So first integral with respect to z introduces the variable z, the function z, from 1 to r. So that'll be r cubed times 1 minus r. The result of that in the integrand is r cubed minus r to the 4th. Now with respect to r, we have this function from 0 to 1. Plugging in 1, that leaves 1/4 minus 1/5 d theta. Right, the limit of integration at 0 is just 0. So we have 1 over 20 is this term, times theta, once we integrate with respect to theta and apply the limits of integration from 0 to 2 pi. So it's 2 pi over 20, and we get pi over 10. So that is another one. Changing an iterated integral in rectangular coordinates first to its volume integral, volume triple integral, and then back to an iterated integral in terms of cylindrical coordinates. Again, the difficult work is done here in this section from the top of that to the bottom of those highlighted regions. And it just takes some vision, maybe some sketching here and there, but just being very clear on what needs to be laid out and which way we need to look at things. Okay, so a final example. we're asked to find the volume of the solid that lies within both the cylinder x squared plus y squared equals 1 and the sphere x squared plus y squared plus z squared equals 4. And what we'll note is that the volume formula is still the same no matter what. It's over a region E. The volume of a solid E is given by, well, the function 1 dV. dV being the volume elements of E, which would be split into an iterated integral. We might write that without the 1 in the integrand. It's just an understood, so we're just dV might be another way to write that. So we have a solid that lies within the cylinder x squared plus y squared equals 1. It's this portion. And we have sphere x squared plus y squared plus z squared equals 4. And we need to think about that for just a moment. We realize that that cylinder has a radius of 1, and the sphere has a radius of 2. So it means the sphere is a little bit wider, a little bit larger than the cylinder, and they do intersect each other along the z-axis sort of centrally, because they're both centered, well, the cylinder has central axis being the z-axis, and the sphere has center at the origin 0, 0, 0. But we realize that the projection of this space onto the xy axis is this circle right here in the xy plane, which is just a copy of the cylinder x squared plus y squared equals 1, or it's all the points that satisfy x squared plus y squared is less than or equal to 1. Or, furthermore, we can write it directly in polar coordinates as the following. It's the region D, so we'll call this the region D, right here in the xy plane, and it's a circle of radius 1. So there's our circle of radius 1 expressed in polar coordinates. So D is written down like that. Now we know that the cap of Z is bounded above by a sort of a spherical cap here and a spherical cap below. And that spherical cap is made up by the upper and lower portions of this sphere here. So we'll solve for Z to get some idea of how it's capped. Can we do that below the work that we did for the region D? These are the surface bounds on Z now. Are they in caps of this sphere? So Z squared, solving for this in terms of this equation, the spherical equation, we get Z squared equals 4 minus x squared minus y squared. Then Z is plus or minus the square root of the terms on the right. And then that tells us that on the bottom, it's bounded by the negative square root of this expression. And on the top, it's bounded by the positive square root of this expression. So we'll know that our surface bounds, a function of x and y for Z, are given by what we have highlighted here. But we're converting to cylindrical coordinates. So we want to take a look and see if we can simplify this quite a bit more. Well, we notice that Z being equal to this is the same as saying Z is equal to plus or minus 4 minus r squared. And that's because, again, r squared equals x squared plus y squared. So we're just converting this term to a negative r squared. Now, once all that's put together, we'll define our region E in cylindrical coordinates. And we have the following. This is just D, and then our surface bounds on Z are given as this. So our integral will travel from Z values of negative root 4 minus r squared to positive root 4 minus r squared, here to here. 0 to 1 for the radius, 0 to 2 pi for theta. And we have r, right? R is introduced by the integral formula. Remember that our integrand is just 1. There's a blank space here that's essentially just 1. And then times the rest of the integral formula, r dz dr d theta, the typical order in this section. We just get lucky with most of these problems that that's the way it'll work out. But we notice one thing. If we look at this picture, we can utilize symmetry. If we cut this thing in half, cut that picture in half, the upper half of this cylinder with a spherical cap is equal to the lower half of this cylinder with a spherical cap, a spherical base, we might say. So what we're just going to integrate from 0 up to root 4 minus r squared. and then double the result of that just to simplify our integrand in z. So to take care of that, let's see how it goes below. Here's our doubling, and here's 0 to the upper portion of this spherical cap. And then our integrand, of course, stays the same. We'll integrate with respect to z. That'll introduce the variable or the function z. So we'll have rz and limits of integration. Remember, this constant is from the symmetry that we decided to do to double our integral just from 0 to the upper portion of it. And applying those limits of integration, we have what follows. That is r times 4 minus r squared to the 1/2. This is a u substitution situation where u is going to be equal to 4 minus r squared. Off to the right, we handle all of those details. We see that u is 4 minus r squared. So negative 1/2 du is r dr. So that will swap out negative 1/2 du, or negative 1/2 times du. And then further, u at the endpoints, the limits of integration is u of 0. So that'll be 4, and u of 1 will be 3. So remember to put those in the order that they should be in. This will be 4 down here and a 3 up here once we switched. So what we see next is that negative 1/2 from the du for rdr. So there's rdr, basically converted and highlighted, times the 2 that was already there. Our new limits of integration go from 4 to 3. And then we're integrating u to the 1/2 du. Power rule tells us that's 2/3 u to the 3/2 from 4 to 3. And then with respect to theta, integrating this. And that leaves us with the constants we see below on the next line. And that is 2/3 times 8 minus 3 root 3 integral from 0 to 2 pi d theta, which is just theta from 0 to 2 pi. And this is just a nice straightforward integral to finish up. And this is decent simplification of the result. So 4 pi over 3 times 8 minus 3 root 3. And that would be the volume contained in this region. Now, be careful using symmetry. It might not always be so obvious. If you're in doubt, just don't use a symmetry shortcut. But this one worked out quite nicely for us. Also, again, we see that the most difficult part is really setting it up and less so the integral that ensues. This is a fairly straightforward integral. Even when we get to here, it's not so bad. U substitutions are really just calculus 1. But using these substitutions to change the limits of integration can really kind of shorten the work too. But it is okay to back out of the substitution from functions of u back into functions of r. It just might be a little bit tedious to do so. Okay. Practice the problems in the book on this one, and see you in the next video.